Hey guys, today we're going to talk about the quantum theory, one of those really cool things. This is just a worksheet for quantum theory. You need to clearly define in your own words the difference between an orbit and an orbital. Well, the orbit is pretty easy. If you think of an orbit, think of an orbit as here's the Earth, and then here's the moon that runs around the Earth. It is very predictable. It goes essentially in a circle or an ellipse around the Earth. We know exactly where it is, where it's going to be every moment. Okay, that's completely different than an orbital. Although they often look the same, we'll put the nucleus in the middle, and then we'll put this circle around it, and we'll say, well, the electron is in here about 90 to 95% of the time. Now when we do that, that doesn't mean that the electron is on the surface of this ball. It also doesn't mean that it's predictable, like we can predict it's going to be right there in the next instant in time. We cannot do that. We can just say 95% of the time when we look for that electron, it's going to be somewhere in this circle. And occasionally we'll find it somewhere else, but the vast majority of time we'll find it in the circle. Okay. So it is a probability distribution of where the electron is going to be. That's an orbital. Now electrons can exist in one of four energy levels. Our four energy levels are S, which is the lowest, P, D, and F. So let's go and fill in this table. The shape of an S orbital is spherical. That is supposed to be SP, H-E-R-I-C-A-L. P's are dumbbell shaped. Man, I'm having a rough day. D-U-M-B. B-E-L-L. Probably only one word. I really don't care. D-U-M-B. B-E-L-L. Dumbbell shaped. The D ones are bizarre, and the F ones are even bizarrer. I'm not going to go and, is that a word? I'm not going to make you remember those. Okay. Now, the number of this type of orbital at a principal energy level, alright, there's one of them. There's one orbital, and remember that each orbital can hold 2 electrons. At the p level, we have a total of 3 orbitals. Each one can hold a total of 2 electrons. That's a total of 6 electrons. The d is 5 orbitals for 10, and the f is 7 orbitals, 1, 3, 5, 7, and that means we can hold a total of 14 electrons at 2 per orbital. Alright, compare the 4s sublevel and the 3s sublevel. Well, they're both spherical. SPH. Spherical. SPH. Spherical. Okay, that means they're kind of round like a ball. Okay, and one is inside the other. So the 3s is inside or smaller than the 4s. Alright. They both hold 2 electrons. 2 electrons. Okay, so those are kind of the similarities. Differences, it's just a difference in size. Alright, the 4s orbital is further away from the nucleus than the 3s orbital. How about the 3s and the 2p? Well, the 2p is closer to the atom because it's got a 2, so it's closer. Alright, but your S is spherical, and your p is dumbbell shaped. D, talk to me. Okay. There is one orbital which holds 2 electrons at the 3s level, but at the 2p there are a total of 3 electrons, each one holding 2 for a total of 6 electrons that it can hold. Okay. So that's pretty much the similarities. They're both holding orbitals. Each individual orbital still holds 2 electrons, but because there are 3, we call them a px, a py, and a pz. Because there are 3 orbitals at the p level, they can hold 6 electrons, but every individual orbital can still only hold 2. Alright, Heisenberg came up with the uncertainty principle. What's the principle, and why does it apply to electrons and not to humans? Well, the uncertainty principle says you cannot predict the speed, the velocity, and the position of an electron at the same time. Well, you can go off, or you can't determine it. Well, you can determine let's say you look at me and you can watch me walk and you can say, where is he going to be? Where is he? I can tell exactly that. I can tell speed, etc. Right? Now the problem is with an electron, you have to find a way to measure it because it's so tiny. So we use light to measure it. The problem is it's kind of like going to you and saying, okay, I want to see how fast you're running, so I'm going to put up a wall in front of you and you're going to run into the wall, and I'm going to see how much effect you have on the wall when you run into it, how much of a dent you put in it, or whatever. Well, that's fine, but that's definitely going to impact what you do when you're running. Well, the same thing is true for an electron, because the only way we can look at an electron is with light, or potentially with other electrons. So we're hitting an electron with another electron to be able to determine how fast it's going. Well, guess what? Aren't we then altering the course of that electron? So that's the problem, is that whenever we try and measure the electron, we have to measure it with something, and that impacts the electron. But when you shine light on us, does that make us move faster, slower? No, not really. Okay, so that's why it doesn't apply to humans, but it does apply to electrons. Right, Schrödinger derived a strange equation. We're not even going to get into the equation, but it talks about the dual nature of an electron. Okay, now the dual nature, what are the two ways an electron can be described? Well, we typically think of it as a particle. It does have mass. Okay, but what we don't think of it of is a wave of energy. And that's where electrons get really cool, because they act like a particle and then they act like a wave of energy, and when they're a wave of energy they have no mass. So that's kind of interesting. Okay? Alright folks, that's it. We're done. Enjoy your day. I'll see you in class. Ask me if you have questions. See you. Bye.